Hello, my name is Anna Castine. This is kind of a crude drawing of me, and I'm your instructor in this Math 1332 Contemporary Mathematics course this semester. I'm looking forward to doing this despite being moved to online. I hope that we have a successful semester, and I will do everything in my power to try and make everything as clear as possible. This first section that we're looking at is about inductive and deductive reasoning. It comes from the critical thinking skills chapter in the book that we have. Remember that you have access to that book through our My Math Lab access. It's an e-text that you can see. You can read through the chapters. If you want to read along or read ahead, it might be a good idea to do so. These notes will follow the structure of the guided notes in Blackboard that I will have posted, just so you know that the structure is similar, but it might not be identical to what it looks like on the page, but you will get all the information that you need to fill them out as you watch along. Before we jump into the notes regarding inductive and deductive reasoning, I wanted to make a quick aside to point out a subset of numbers that we're going to be talking about and looking at kind of intensely this first section, and that is the natural numbers, which are also called the counting numbers. So the natural numbers or counting numbers are the numbers 1, 2, 3, 4. It's literally the numbers that we use to count quantities with. So it starts at 1 and it continues onward. After 4, I'm going to write 3 little dots, which is called an ellipsis, that shows us that this continues onward, because obviously the counting numbers don't stop at 4, they go on forever and ever. The next thing we want to look at is what it means for two numbers to have divisibility. We can say that A is divisible by B if I do A divided by B and I get a remainder of 0. Okay, so for example, if I say 15 divided by 5, that gives me 3 with no remainder. So 15 is divisible by 5. Okay, so that is one thing we need to know. And then the last quick fact we need to know is what are the difference between even numbers and odd numbers. Our even numbers are all of the numbers that are divisible by 2. Okay, so that's going to be, just skip counting by 2, we can list them. 2, 4, 6, 8, etc. Again, those go on forever. And odd numbers are the numbers that cannot be evenly divided by 2. So that's going to give us 1, 3, 5, 7, 9, etc. And if you are very interested, a quick thing you might want to check, and I'm going to ask that you do this on your own, is 0 even? Okay, curious question. See if you can figure out the answer. So just stating now, 0 is not a natural number, so it's not part of the counting numbers. It's part of the whole number system, but we're not looking at that yet. But ask yourselves, is 0 even? Just curious. Okay, moving on. We're going to take a look at inductive reasoning, which I have abbreviated IR. Okay. Inductive reasoning is the process of reasoning to a general conclusion through observations of specific cases. So we're taking specific cases and making a generalization. Okay, so we're looking almost for patterns. If I find a certain pattern, I can make a generalization based on that pattern. An example of inductive reasoning might be the answer to the question, if an odd number and an even number are added, will the sum be an odd number or an even number? So if I take an odd number and I add to it an even number, okay, will the sum end up being even or odd? And then we look at a couple examples. So we pick an odd number. Let's pick 5. And then plus an even number. Let's pick 2. 5 plus 2 equals 7. So that's odd. Okay. Let's try another one. An odd number. Let's do 11 plus 6. 6 is even. 11 is odd. 11 plus 6 is 17. If I let's take 21 plus 8. 21 is odd, 8 is even. When I add them together, I get 29. Now, 7, 17, and 29 are all odd. So based on these specific examples, okay, I could come to a general conclusion that this would be odd. Now, can we prove these conclusions to be true or false? With inductive reasoning, if we only have those specific examples, it only takes one counterexample to prove it false. Okay, so we say that inductive reasoning we cannot prove our conclusion because all it takes is one counterexample that could prove it wrong. Looking at deductive reasoning is the process of reasoning to a specific conclusion from a general statement. So with deductive reasoning, we're going from a general statement to a specific conclusion. An example of deductive reasoning would be if I were to say all organisms are made of cells. Made of cells. Humans are organisms. Therefore, humans are made of cells. Okay. In math, that is actually going to kind of look a little bit different, but the idea is that if you can prove something in a very specific case, and in general it is always will be true, then you'll have used deductive reasoning. Okay. With respect to the last question, can we prove conclusions true or false? It's actually the case that mathematicians use deductive reasoning to prove conjectures are true or false. So this is the kind of reasoning that mathematicians use. Inductive reasoning is actually used by mathematicians and scientists to develop theories and to predict answers to complicated problems. So while they might not be able to definitively show that it's proven true, they use inductive reasoning to look for the patterns and then come up with a hypothesis or conjecture. But deductive reasoning is what we use to actually prove something is true or false. And remember that inductive reasoning can be proven false using just one counterexample. So let's take a look at some examples. The first example is asking us to use inductive reasoning to find the next numbers in these sequences. So I look at this example and I see 19, 24, 29, 34, 39. If I'm looking at each of these, I try to figure out what's the pattern between them. How do I go from 19 to 24 and from 24 to 29? And is there a consistent pattern that's happening? And when I look at those, I see that each time the number is being increased by 5. So the next few numbers, I just have to add 5 to each one. So I'm going to get 44 and 49, and I could continue and get 54, etc., right? The pattern is we added 5 each time, okay? Looking at the second one, I have 2, 8, 32, 128, 512, and I don't see a consistent additive pattern, but if I look at this, how do I go from 2 to 8? Well, if I multiply by 4, 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. So I can see that to find these next two numbers, I'm going to have to multiply these by 4. I'm going to get some really big numbers. So now is a handy-dandy time to take out your scientific, because that's the only one you're allowed to use in my class, scientific calculator to calculate those remaining numbers. Doing so, I end up with the values 2,048 and 8,192. And the pattern is we multiply by 4. Okay, now I have 1, 4, 1, 7, 1, 10, 1. To look at this one, you might pause for a second and be like, well, we're going up and then going back down and going up and going back down. And you might try to look at the pattern in different ways. The way I'm seeing this one is I see plus 3, minus 3, plus 6, minus 6, plus 9, minus 9. And following that pattern, I would assume that the next value would be plus 12, minus 12. So 1 plus 12 is 13, and then I'd end up with a 1. So then I'd do plus 15 minus 15. Okay, so that's one way I see this pattern. Somebody else might say, oh, well, every other number is 1. And then starting with 1, and then every number after is increasing, every other number after that is increasing by 3. So 4, 7, 10, 13. So you could also see it that way. And so then you want to determine how do you want to describe the pattern. So I'm going to say add 3, subtract 3, add 6, subtract 6 for all multiples of 3. Okay, you could describe that another way that makes more sense to you, but that's how I see that one. Okay, I'm going to switch to a different color just because I got a little bit out of my zone on that one. And I have the pattern 1, 1/2, 1/3, 1/4, 1/5. And we can see that the denominator is increasing by 1 each time. So if you think about it, 1 is the same thing as 1 over 1. Okay, so here I have 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5. So following that pattern, I'm going to end up with 1/6 and 1/7. And I would say that the denominator, which is the bottom part of the fraction, increases by 1. Okay, and then this last one, we have 2, 5, 9, 14, 20. And you might see that this one increases by 3. These from 5 to 9, it increases by 4. From 9 to 14, it increased by 5. From 14 to 20, it increased by 6. So I'm going to assume that this is going to increase by 7. And then the next one would increase by 8. So 27 plus 8 is 35. So the pattern would be we add by 3, and then you can think of it as 3, 4, 5, 6, etc. Or you could think of it as add by 3, 3 plus 1, 3 plus 2, 3 plus 3, and so on.